Hello there. We have a new topic today. It has to do with electrostatic energy. And here are three illustrative problems that kind of span types of problems that can show up when dealing with electrostatic energy. So first you should be clear what is electrostatic energy. So this is the energy where charges are not moving. Okay, so if you have, say, a charge here and it's not moving, so this is a plus charge, it's not moving and it's just sitting there, then you can say that there are electric fields emanating from here. That's all you can say, right? This one charge. So now if I move this charge from, say, point A to move it over here to over there, it doesn't cost me anything because I don't have to oppose anything. There are no other charges. So this universe is a very strange universe. There's only one charge in it and no other charges. So it's really doing, I don't have to do anything. Now you say, okay, how about magnetic field? Well, when I move it, I'm going to move it so that it's move it in a way that it doesn't interact with the magnetic field. There's no velocity, but it's kind of ideal. So it's kind of pseudo movement. I just move it conceptually. So going from here to there, I don't give it any velocity, no kinetic energy, no nothing. I just move it as if it was here and then somehow it is over there. Okay, I don't impart any kinetic energy to move it from A to B. So no work is done from me, and so no whether it's at A or B, same energy. So it's like not very pointless to say how much electrostatic energy is here, although there is a point to it, because you'll see when the charge is let me back up a little bit and say, imagine a universe that no charges, but there's a point A, no charges. Okay, and then imagine a universe that has a point, this charge Q at that point A. The question is, these universes have different energy? And answer would be yes, because this universe has no electric field, is 0, and this universe is filled with electric field, and so these two universes are different. So you'll say there is electrostatic energy here, but we are going to talk about electrostatic energy with respect to this energy, right? All right. So let me explain some of the problems here. So problem one is, suppose I have these three charges. They were far away. So maybe it's over here and I bring it here. Maybe it's over here and bring it here, here. So I assemble these charges from the infinity. How much work will I have to do? So that's a question for you. Maybe you want to answer that. And then you can use this technique that you have it here and apply it to a large number of ions, not just 3, but large numbers of charges. Okay, an example will be like a crystal, like sodium chloride crystal, which is the ionic crystal, and which is plus charge and minus charge are alternating. So this is minus, this is plus, and this is minus, and this is plus, and then this is minus, and back there will be plus because that neighbor will be minus. So this thing will go on forever. And so can we figure out how to apply this? Well, the work that I have to do is the amount of energy that this will have compared to the charges at infinity. Then comes the capacitor. How do I figure out how much energy it will take to say, so this question is, say I have a plate A and another plate B. Initially they don't have charge, extra charge, and then I do this. I take electrons from here and put over there. So this becomes a plus charge, this becomes a negatively charged, and there will be lack of electron on this side. So this will be in the end negative charge. So this will be minus, this is minus Q and this will be plus Q, because there will be excess extra proton here compared to the electrons. Over here there will be extra electrons compared to the protons. And so if I starting from uncharged, so A and B were uncharged, from this state I want to go to that state, how much work it will take, and that was the amount of energy that's stored over here. Okay, so if you want to do this problem out, that's fine. I'm going to handle one at a time. Okay, all right, so okay, so you know that the basic here is very simple. Basic is, suppose there is a point, some point here P, and at this point the potential from all other charges, so V, it's from these charges have potential, by add them up, etc., find some potential here. Now if you have a charge, new charge, when you bring from infinity, V here is 0, so this is at infinity. When you bring it over, no matter what path you bring, and you bring it over here, then amount of energy of this guy will be just Q times that V. So Q nu times V is the amount of energy that will take you to get here. So say I had a positive charge and you want to bring a positive charge from here over here, right? So you bring it over here, and this somehow you virtually hold it fixed. You say, well, I'm bringing it there, it's going to also push this away. No, I'm going to just assume it's fixed. It's just a technique, mathematical technique when you use. So this is Q nu, and from this guy had a potential V by, say, Q old. This is Q old. Okay, so you can see if this is a positive, this will be a positive potential, right? This will be positive potential. So amount of energy I will need, amount of work I have to do is Q nu times VQ. So that's the amount of work I have to do. So what if it was this will be positive work? If I had a negative charge here, and say Q nu was negative, I brought it over the same place, the amount of work that will be Q nu is still VQ. But because this is negative, so this work will be negative, which means I have to take energy out. So if they're, if this is positive, this is negative, they're further apart, there's an energy stored in them in separating positive and negative. But if you bring them closer, you have to extract that energy out by doing a negative work. Okay, so I'm going to just apply to that, and I'm going to assemble these one at a time and see what happens. Okay, so let's see. I'm going to start from here. Start this guy. So I'll start this guy. Bring all of them. Then I'm going to bring this guy. Then I'm going to bring this guy. They're all same, but I'm going to label them 1, 2, 3. So I'll bring Q1 here from infinity. There's no charges here to work against. So the potential was 0 initially. So the potential, so it was 0 There was no other charges. So the work I did was, let's call it work 1, to bring this guy, I'll just call 1. I just had Q1 time, there was nothing, so this is 0. So now I'm gonna fix it. But there's nothing else in this world, so this I have to do so-called virtually. I have to fix it. Use math mechanism. Okay, so there's several ways to say it. Just I fix it, and I bring Q2 from way out to here. The distance A from here. Well, distance A from there, this guy is creating V. V at this point is going to be Q 1/4 pi epsilon naught Q over A, right? Because that's the potential is going to create. And then when the number 2 comes in over here, W2 comes in over here, you have a Q2 times, this was Q1, I bring Q2, so it's going to be this thing, V by 1. So V by 1. That's the only charge there. Third charge hasn't come yet, so this is the only thing, right? So this is going to be 1/4 pi epsilon naught Q1 Q2 over A. So that's the amount of work I have to do. Now I'm going to fix this also. Now I'm going to bring at that point the third charge from infinity. But at infinity it has 0 potential, so energy that I will need to work will be potential by this, potential by this. So what is the potential here? Potential now on this point will be potential by this guy plus potential by this guy. So this will be equal to V by 1 plus V by 2. And each one has the same expression like this. So this can be W3 will be Q3 times V by 1 plus V by 2. Now I've assembled it, so now it's complete. So I need to add these guys up. So W net will just be W1 plus W2 plus W3. That's the amount of work I had to do. And that's just going to be, you can see that 1/4 pi epsilon naught. And you have a Q1, Q2 over A plus Q2, Q2, Q3 over A plus Q3, Q1 over A. So you could see the pattern going is all pairs, right? And the distance between them. So this is like a, if you want to kind of write some kind of general formula, it's going to be like a 1 over sum over all pairs and 1/4 pi epsilon naught all pairs once. So I don't have a Q2 Q1, so you just have a Q1 Q2, and if you do Q2 Q1, then it's not a separate term. Don't use a separate term. So it's like a half of all the pair of all pairs. So just all pairs counted once. Okay, 4 pi epsilon naught Q Q times Q of the pair over the distance of the pair. So this is what the amount of work. And when you think like this, you should be able to write a formula for any other combination, right? Like the sodium chloride thing. Okay. I hope this is clear to you. All right, let's do the next one. Okay, so the second problem, I'm going to change it. I was I was thinking I would do some solid state physics, but it's a little bit advanced for this course right now. So I'm going to change that to just what is called unit cell. So there are 8 vertices in a cube, and sodium and chlorine ions kind of alternate. You probably know that from chemistry, and I wanted to get apply our technique to this. So you can see right away that there are several distances involved when I apply this formula. So so this formula will be like electrostatic energy U will just be equal to sum over pairs and Q times Q, Q1 and Q2 of the pair, and the distance between them R1, 2. So of one pair, you just go to pair and multiply their charges and divide by the distance between them, 1 over 4 pi epsilon naught. So that's what we got from doing a simpler problem, right? You can write it many different ways. People write it like I and J, and let's call it I, J, and this is I, J, all pairs. Okay? Whatever suits you. It's just a way of writing and talking about this. So if you look at this, this will all be E square, right? So Qi, Qj will all be plus E and minus E. This is the full charge on sodium, full on chlorine, and so this is minus E square. Okay. How about the distances? Well, so if I go between here, from this to this and this and this, so there are 3 of these pairs that are distance A. So these are A and A and A. Then I go to the face corners. This is the opposite. So this is minus plus distance is 3 of them. Okay, and then I can go to the face, these faces. That's where the opposite faces. There are also 3 of them, and they're going to be square root of 2 times A, and this is going to be minus with minus, and there will be 3 of them. Then there is a pair which is let's use a different color. Then this is a minus with a plus, and there's 1 pair, and that's a square root of 3A. This is a body diagonal. Now that was starting from here, right? So we took care of all the pair that has this as one of the, so let's call it 1. So this is all with 1, has 1 in it. Then go to 2 that does not have 1 in it. So let's call this 2. Well, if I go to 2, this is the only thing that doesn't have 1 in it, and then all of them will be, so from the 2 you'll be one of the A's will be missing, right? Then you have a plus with a minus, you're going to be 2, and then plus with a plus is going to be 3, and then plus with a minus will be this way diagonal over there. So this is going to be A, square root of A, and square root 3 of A. And then done with the 2, then say this, I call it 3. Now 3 should not have this already included in here. So one of the body diagonals on one of the sides is not there. So in the 3, so we don't have this. A is only the plus with the minus, only 1 left. 2 left, I think. Yeah. This and this, yep. 2 is still. Just the body diagonal is instead of 3, now we got it, only 2 of them is equal to A plus with a plus, just 2 left. And then this one doesn't include 1, 2, so I get a is equal to 3A plus with a minus, this guy's with that guy over there is 1 left. So 3 done. So you can see I can do 4 here. This guy is 4. So 4 with 2 and 4 with 3, they are sides. So thing that includes 4, side will be only 4 is minus, so minus with a plus is going to be only. So from here you get not 3, just only can go to this point, that's it. So that's 1. And 4 with 1 is a face. So I need 1 less face. Square root 2 times A, and face will be only 2, and is equal to 3A. Now from here you go all the way, bar diagonal is there, that will be included, minus with minus, and if this is plus and this is minus, then only then this is minus. If this is plus and this is plus, then this is plus plus, that's E squared. If this is minus 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 minus, then this is plus E squared. So we gotta have different signs for different terms here. I just noticed. Now we can go 5. This guy is facing 1. Start from there. So now I can't have 4. 1, 2, 3, and 4 because I already included them. So if I go from 5, 1 is a side, but the other 2 sides included. So the A will be with a plus and minus. There are 2 of them. And when I go to face, 2 is a face, 3 is a face of the 5. So 2 and 3 are the faces. So square root 2A is only going to be 1. How about diagonal? Diagonal already included in the 4 is the diagonal. So square root of 3A is 0, not include. So not include. It's already here over here. This thing is a diagonal to that. So if I go to 6, this is 6. You can see there's only, I don't need to do a whole lot. 6 can be just 1 this and 1 this. 6 will be A with a minus and plus just 1, and square root 2 of A minus with a minus is 1. That's it. And if I go to, this is 7, 5 included already, 6 already, so I just can go into 8. And A, 7 was minus, minus plus is 1. The diagonal, face diagonal is already done. However, the body diagonal will be on the other side, is already done. So if I go to 8, if this is 8, already everything is done, so nothing. So now you can see you can just add them up, right? So I know a lot of terms to add. You can see this will be 3 terms like this, 3 terms like this, 1 term like this. So let me just see if I can add them up. All right. Okay, so U has terms like 1 over 4 pi epsilon naught, and then either you're going to have a e square over that, and either it's going to be minus 1 these guys, or you're going to be minus 1 over a square, or you're going to have a plus 1 over a square. They're not, this will never happen. Okay, or you're going to have a plus 1 over 2a square. The phase diagonals, and the body diagonal is always going to be opposite charges, minus 1 over 3a square, right? So how many of each you got? So you got 3 of these, and plus 2, this, plus 2, plus 1, and plus 2, plus 1, and plus 1, right? So all of these are opposite. So that's how many of these is going to be. So 3 times, so this is 8, 8 and 4, 12. So this, you got 12 of these. So we got done with that. How about these guys? Actually not a square, it's just a square root 2a square root 3a, not a squares. I don't know why I squared it. Now counting these guys, 3, 2, 1, and 1. So 6, 10, 12. This is 12 too. So this is interesting. Okay, hopefully I counted right. Okay, so now the body diagonals will be let's see, 1, 1, 1, 1. I think it's all about, there are only 44 body diagonals, so this is 4. So that's the answer. Okay, hopefully my answer matches with your answer, and important part is to look at how I have applied it. Okay, let's look at the last problem, which is continuous charge problem, but applying the same technique. Okay, so finally we come to a problem 3, and in this problem we have continuous, instead of just one charge at a time, we have some amount of charge transformed from one place to another. All right, so our problem is to have a plate like this and I have another plate like that. So initially this is they don't have charge, and we want to find, if I keep removing, say, some electrons from here over there, and this becomes negative, this becomes positive, then in the end it's going to be, say, minus Q, and this plate or this conductor becomes plus Q. Then how much energy we are talking about in terms of doing our work. Okay, so if you look at it, at some point it's going to be a charge Q over here, minus Q over here, and it's going to be plus Q over here. And the voltage difference between them, so if you think about the voltage, this will be V equal to 0, then V equals to, let's call it V sub Q when the charges are Q. So V sub Q is just 1 over C times Q. This is from the capacitor formula. You should remember this, that anytime it is minus Q plus Q, then the voltage difference between them is given by, at that point, is like that. So if I do an infinitesimal step, what do I mean by that? I take a very few electrons and transfer, and let's call it the charge as dq. Then at the end of this transfer, this will become minus q minus dq, and this will be q plus dq. And the voltage difference, how much work, so this is basically, if I can figure out how much work I did here, I can just integrate and get that, right? So how much work I did here? Well, when I transferred, the potential was this. So potential times this amount of charge will be the amount of work. So in this will be like a du in this step. Let's call it infinitesimal amount of work in this step by du. This will be just amount of charge I transferred, which is q, when what was at what voltage difference did I transfer, right? So vq. So that will be the amount of work I will need to go from point 1 to point 2, state 1 to state 2. But we're not interested in this. We're interested in when the q was 0 to q equal to plus q. We want to integrate from here to there. Over here, the potential difference was 0. Over here, the potential difference will be, whatever V capital Q. So let's label the potential with the charge that's on the plates, okay? So basically I need to integrate this. And how do I integrate this? So U, delta U, this is the amount of work I need to do, is this integration of du. And so that's a VQ dq, and this is the integration variable. So that's initially 0. So this is from initial to final. So this is my initial state, and this is the final state. So from the final state, q has to become capital Q, but this thing is not constant, cannot come out of the integral. So this actually is 1 over c times q over here. So now I write this down, 0 to q, 1 over c q dq. And this is constant, can come out, and this is very simple to do. This is 1 over 2 q square over c. So that's the answer. But over here, if you can see that VQ is 1 over CQ. That's also coming at any stage, it's going to be, that's the voltage difference. If I want to write in terms of voltage at the final voltage difference, I can use that, and it's going to be 1 over 2 C V at this is the final voltage square. So that's the answer. Okay, this half comes because I had to do this integration over here, right? So that you understand. Another way to actually see this half is to see this plot. When you plot this V and Q, what's the voltage and how much charge you plot. So it's going to be this is the V final, Q final. So it's the area. This integral is basically area under this curve, and that area under the curve of a triangle shape will be half base times height. And you can see over here, if I take one of the V's separate out, that's going to be half CVQ times VQ, and so this is the Q times VQ, and that's what that is. So there's a couple of ways of getting this energy stored in a capacitor formula. Sometimes you will see you're given a specific capacitor and like a parallel plate capacitor, and you have to say what the energy stored in the parallel capacitor if I put a voltage V across them, and you just have to kind of apply this formula in that situation. Okay, so don't forget to subscribe if you haven't subscribed. If you like this kind of explanation, from basic physics and using some math, hit the like button. You can check out my website also. So I'll see you in another video. Bye.